NPTEL schedule. Okay, so good evening, everyone. Uh, I guess I am audible. Yeah. So let's start our live session. So we can start with this question. So in previous classes also we have done this kind of exercise. And so this question is about electricity, and we have learned about this thing. So what is electricity? So we can say the special arrangements of methyl or any R group which is present in this position, and according to these two relation, we differentiate between the arrangement. So there are three classes we know actually. Diatactic, atactic, and isotactic. So we have learned that so for isotactic, all are in the same plane, like above, all are in above. Then it is called isotactic. If let's say you have this kind of arrangement above, below this kind of racemic diads, so then you can call this kind of relation as indiatactic. And if there is not at all any pattern is there, means uh, above, below this arrangement can be anything. So uh, there is no such pattern. So then only we can call them as atactic polymer. So for toxicity, what is needed is having a chiral center over this position. Means if your monomer should be pro-chiral like this, so then only after polymerization you can create this particular center, which is now a chiral center. So the basic need for this kind of observation should be your presence of one prochiral center. Now they ask in this question is for which case you would not observe any plasticity. So we should look for some uh, monomers where you do not have any prochiral center. So now let's look at the monomers of these polymers. So then only we can decide. It is polyvinyl chloride, so well known. So for here we have vinyl group. So let us see, this would be your monomer. Now if we look into this monomer, this is the prochiral center. But after polymerization, you are going to generate kind of system. So these centers are chiral center. In that way, this above or below can decide the class of this kind of polymerization and distribution decide. So for this particular phase, you are going to definitely observe toxicity because you have chiral center. So A is not B yours. Now we the polystyrene. So there styrene group will be there. So means your monomer would be this way. It's styrene. Normal styrene to when you polymerize it, again it is a prochiral center. After polymerization, you are going to see this kind of polymer formation. So now these two are again chiral center. So due to presence of this chiral center again, this kind of pattern you would definitely going to see, and flexibility should be there. So B again should not be an option. For polypropylene, the same case. So there we have propene unit as monomer. So when we do the polymerization reaction, so here methyl would be there like this. Again, chiral centers are present. So same thing would occur like previous two cases. So toxicity would be there like this, and this would be having some toxicity in your microstructure. Now, lastly, the equation polyethylene. Here, as both of the LCs please to show these are not prochiral center because after polymerization, you are going to generate this kind of chain only, and these are not chiral center. So there is no chiral center is present in this kind of polymer. So toxicity would not be there. So that's how you can decide the D for this polyethylene case. The toxicity you are not going to see because there is no chiral center present in the entire polymeric chain. That's a way to solve this kind of now coming to this one. So so there they asked about organometallic polymer. So it is very easy. Now we have learned and read many things about this kind of catalyst. So this kind of thing. So this is the sandwich molecules we have read. Ferrocene type scaffold is there. So it is a organometallic molecule, obviously. So for the first case itself, we are seeing that it is a organometallic solid because organometallic part is there, and here the repeating unit is there. So it is that way it is polymer and organometallic. This uh, bond is there. So it is the organometallic polymer. We see this kind of cases. So here only silicon oxygen bond based. So inorganic polymer, it is also inorganic polymer. So they are not correct. So the right option will be this, where you having this ferrocene unit, and for which we can call it as organometallic polymer. Next question is they want to know about is the correct option of for which Sarikawa, Higir, and Mac Diarimi, particular these three people, received the Nobel Prize for 2000. So it is again information-based question. So you need to know about these things. So if we just look into the Nobel Prize in 2000, so these three scientists they are talking about. So for they actually won the Nobel Prize year in chemistry. So their key finding was how can that plastic become conductive? So plastic we know they are not conductive electricity, but how it can do that. So that's the key thing about the discovery. So here is a small statement, and there they are saying that plastic are polymers, so molecules that form long chain. So polymer, what we are learning and reading through these classes. So repeating themselves like pearls in a necklace. So the monomer they are talking about. So with small monomers, when we attach them and make a big chain like this, so that is called polymer. So they are so it is an organic molecule, so no metal is there. So it should not conduct electricity, right? So that we are talking about. And so that's their key finding. So how they can behave as metal. They want to imitate metal, and they want to uh, this free flowing electron that can present in these cases. How for metal units, what we see that. there are electrons are there, so as they are easy to move around, so they can easily conduct electricity. So this particular property they want to incorporate in your this kind of organic based chain system with polymers, so that can be used in various fields. So the first condition for this is polymer consists of this alternating single and double bond. Means this kind of chain is needed to do that, because then only electron can migrate from one place to other. Because you see here, so this kind of thing is needed, how we do the resonance thing, so that electron also can migrate like this and it can conduct electricity. So that's their key idea, and for that they have developed this particular uh, um, polymer, polyacetylene. So this one they have prepared to polymerization of acetylene. So for with acetylene they have done their polymerization. Yes, for this case acetylene is their monomer. Now after that they have designed this kind of uh, system where the double bonds are actually e double bonds they have made, and they have uh, designed this particular thing for this particular electroconductive application. Now they have now dope with polarons. So in first Weber reaction, so oxidation. So with iodine molecule, they have polarized this one of the double bond. So one polarization is needed, initial polarization, so that you can generate one charge, and that can now move with the principle of resonance. So we just need to, or they just need to develop one positive charge in the system. Then only the electro or conductance that they want to generate in plastic, that can be done. So for that, they have used iodine molecule. So that attracts one electron from the polyacetylene chain and becomes I3 minus. So when this polyacetylene is reacted with iodine, so they observed oxidation and iodine becomes I3 minus. So one of the electron is captured by iodine and it becomes this I3 minus. So it got reduced and the double bond or this system got oxidized. Now this polyacetylene molecule is positively charged. In the animation, they have shown, and you can easily understand like this. And they term this as radical cation or a polaroid. So when it is treated with iodine, you can initially generate. So this is the initial state. Iodine captured one electron, and here again second electron. Now you have this double bond, sorry, positive charge, and this can, in this way it can migrate from one end to another end. And so that's basically flowing of electrons from one place to another, which is the key principle how to make material conductive and how metal conduct. So that's the principle, and in that way they imitate that in basic organic molecule in this particular polymer system. So that's the key finding of these three people, and for that actually they got Nobel. Now coming to this, so now we can see the options and we can decide the answer. So discovery of alkene metathesis. So it is not discovery of conducting polymers. So B option, the conducting polymers. For that they have given the Nobel Prize. That should be the option. And isotactic polypropylene not one and macromolecule. So B option would be right. And we have now discussed this how they have developed this kind of so Again, it is information based, so you need to know that. So the polymer present in soda. So for that, option would be this one. So polyethylene uh, terephthalate. So this particular polymer, it is particularly used for fundamental. So the structure, if you see, this one is a structure. So for this actually, the monomer units, let me write it. So here, for this, we have two monomers actually. So the repeating unit is this thing, DMT or dimethyl terephthalate. So structure, let me write. This is one unit, dimethyl terephthalate, and this diol unit. In glycol, they have used actually, and uh, the processes here. Uh, It is actually these two are taken and it is treated in raw means in, no solvent is used, only these two reagents, 150 to 200 degree initially, and lastly it is prepared up to 220 degrees centigrade to 360. So these two that way reaction is done. So initially what happens is two units actually provide for mm, two stories and here also kind of here one issue. Yeah. This kind of might get first formed, then it got polymerized. And ethanol is byproduct here, and with this high heating condition, it is actually removed from the system. In the second step, your polymerization happens. So number of monomers got uh, polymerized, and you have kind of what it is written like this. So polyethylene terephthalate, this particular polymer, they are produced like this way and they are used for this protocol. So coming to next one. Here, the question is what will happen if crystallinity increases for a polymer in a solid state. So, if crystalline property increases in your polymer, so both density and young modulus should increase. So, the density should be increasing. So, it is crystalline property increases. And if it is denser, so young modulus should increase. It this way we can understand. So the C would be your option. So solubility and barrier property uh, would again increases, not decreases, and mechanical strength will increase. Young modulus will increase, which is wrong, and uh, so which is a contradictory statement because if density increases, the optical clarity should increase. Here I am saying it is increasing. Again, it's not correct. Uh, that's why the C option for this one is the would be your option. Now, for high density polyethylene, they want to know the correct statement. So let's look at the property of first high density polyethylene. And so high density polyethylene, so known as HDPE, are polymer whose generally the monomer is ethylene units, and it's thermoplastic with very high strength to density ratio, and they are very versatile plastics actually, and their application is can be used in you can see in the many day-to-day uses like pipe, storages, bottles, and when compared to other plastics, the melting point of this kind of polymer is relatively steep. So that's the basic, if we can say, property for this kind of high density polyethylene uh, polymer. And for these are again some of the properties. So they are flexible, translucent, waterproof, and good low temperature toughness. Doing low temperature, they are uh, tougher compared to other ones. Easy to produce by most of the method because here again you are seeing that no issue of that branching thing. So it is pretty much easier for production of this kind of polymer. And they are low cost and good, obviously, chemically ready. And so these are the properties of HDPE. Now for low density polymers, what happens is lot of branching is there. So here you are seeing this kind of polymer. So the density can be higher because the chains can be closer to each other like this. So their density is higher. But when we have this kind of so much branching happening like this way, so then two polymer chains they cannot come very close to each other because of this highly branched structure. So they repel each other, and there you have lower density, and accordingly the different properties like flexibility, translucent, this thing obviously going to be hampered. So that's the properties for low density polyethylene molecule. And LLDP, so for that, that obviously branching is there, but they are branches slightly shorter compared to your LDP. So in that way, we can actually decide things. So with this microstructure, it obviously going to affect uh, the ultimate properties that you are looking for your material. So with this kind of things, with microstructures, you can vary and you can differentiate the properties, and with that, the different uses we can uh, maintain or manipulate. So according to your needs, what you are looking for, what kind of plastic you want to make. We can decide this, and ultimately, uh, that particular property you can make. So that's how it's actually decided. So coming to this question, so not this is not correct statement for HDP. So firstly, they are talking this linear structure with large number of shorter branches. So they are linear structure, but we just look at that branch should be short. So or at all, no branching is there for high density polymer. For LDP and LLDP only, we use for branches. So for short branches, specifically, it is for LLDP, not HDP. So this is not a correct statement. So they are looking for that one. So A would be your one of the. Now let's look the other option because it can be MS2 type also. So it possesses high degree of crystallinity. So here we have uh, see this particular thing there. Crystallinity is higher, so it is correct option. So you can remove this one. Now it is a thermoplastic polymer again. Correct statement. It is also HDP and rigid in nature again. Correct. So B, C, D, these particular statements are correct. And we are looking for which are not the properties for HDP and option B is correct. Now coming to this, so what is the chemical structure of purification unit of polymethyl methacrylate? So this is your polyethylene methacrylate polymer. So and this is the monomer unit, the repeating unit. Now how this monomer can be? So what is the monomer? You can just correlate with the option. So now let's look at, so here the phenyl ring is present. It's not because it is for uh, uh, polystyrene particular polystyrene unit for this kind of structure you can see. So not this one. So for this it's close, but here we need one methyl group. I mean only you can call it as methyl methacrylate, but it should be only it will be polymethacrylate. The methyl unit is not B. Again, cyano not right, only D. So for D, you are seeing that methyl unit and ester unit both are present, so that's why it is missing and D would be your option. Now, for this case, they are asking about the right option of for elastomer and thermoplastic technology. So at first we need to know then what are the thermoplastic and thermocoating polymers and the elastomer. So for the physical difference actually between these two thermoplastic and state parts, how the materials behave during heating. When it is heated, then only we can actually differentiate between these two particular polymers. So for thermostats, it is seen or it is observed that they are strengthened, means they are we can see the hardening. So for this kind of to form the chemical bonds that make them impossible to remove, means they cannot be broken. This for thermo set polymers, so that chemical bond. So that's why they self conducts and hardening we can see. For thermoplastic, there is no chemical bond in the cooling process, and it is remountable and recyclable, and uh, that three-dimensional bonding for thermostats become makes them stronger and more heat resistant than thermostats. So here you can see for the basic uh, microstructurally different. So this is the polymeric chains like this it is present, and the only weak intermolecular forces like van der Waals forces or like entanglements like that only is that way. For thermoplastics, it is only present. So the basic attractive force between two sets of polymeric chain is only this intermolecular force. So no sputtering is there. So that so for that when it is heated, this kind of properties you can see the melting and reboundability, recyclability, this kind of process we can for when thermosetting is there. So for that, here you are seeing between this polymeric chains, intermolecular strong cross-linked bond is present, and they are chemical bonds. No, not intermolecular, just force of attraction, they are chemical bonds. So that's why that strong covalent bonds are present between polymeric chains. So that's why the strong or that hardening property comes with for this, and they remains hard when it is heated. So that's what thermosetting polymer. So now we can use the options options of elastomer and thermoplastic polymer. So the thermoplastic polymer becomes liquid when heating. Sorry. Thermoplastic become liquid on heating. So that's the thing what we have seen here. So why it is happening? Because of there is no chemical bond is present between two different cells, and for that they actually liquefy on heating. So uh, it would be your one of the options. Yeah. HDP is not elastomer again. This really highly dense. So previously we just read about HDP and their properties. So they are crystalline nature is there. So they are not elastomers actually. You can move this, then amorphous courage and so elastomer they are soft in nature. This two option will be the lactose. Now continuing that previous question, previous question. So you are just learning about elastomer. Now and so the definition is written here like this. So an elastomer is a polymer when his co elasticity means both viscosity and elasticity and the weak intermolecular forces generally low young modulus and high failure in strain compared to other materials. So these are the basic properties that you need to have for your polymer. Generally, you can call it elastomer. So basically, elastomer is obviously a polymer with low with both viscous and elastic this property, which also having this intermolecular force. So that's the thing. So that's why we have written here like this. So they are soft in nature and the young modulus is low. And yes, the way to decide them. And for here they are asking about again that thermoplastic and thermosetting these things. So now let's look at thermoplastic polymers become liquid when they are heated. So this is the thing what we have seen here, right? So uh, we have seen over here, and so the cutting process what we are talking about is like this. So they are actually heated. So that's the thing. That's the main thing about this particular process. In this, here you are seeing that three zones are there. So in the zone one, viscous liquid. So unreacted monomers and cross-linking agents from a small branched molecule. So with the monomers, when it is heated, so this kind of branching and polymer formation is started, and gelation is there because the polymerization already started. And in the zone two, a giant macromolecule appears that uh, circulates to the sample. So the chain which is growing now that become macromolecular, very long and a pretty gel kind of nature. It goes. And lastly, when wood, this kind of thing, when that cross-linked polymer, when it is formed, then it becomes glassy solid. So that's the thing for thermostatic, right? So for thermoplastic, there it will become liquid, and for thermostatic, it becomes glassy solid. So that's the verification phase. That's why it is called verification phase because if thermoplastic polymers is heated in this particular zone C, you can see that liquid formation, and for thermostatic polymer, you can see this kind of glassy solid formation. Solid formation would be happening in zone 3, and for thermoplastic, you will see liquid formation. So that's the way to verify or differentiate between these two properties, these two polymers. So for thermoplastic polymer, it become a liquid when heated. So that's the one. So thermoplastic polymers are more fast. So we cannot conclude this particular statement because they have different natures. So amorphous is not one of them. And thermoplastic polymers may be semi-crystalline with both crystalline and amorphous domain. So both of obviously both the things can be present. So that's why WGL, this kind of properties are there actually. If you use your option and their thermostats are something nature. It's not a true statement because they are solid and high young modulus is there. So that's what we have seen. So A and C would be your option. Now for this case, they want us to identify that correct options for uh, polypropylene. So I so that's it in the so different that's we can be present for polypropylene because monomer unit is like this. It's a prochiral center, and in the chain you would definitely going to generate this kind of chiral center, and radiation would be there. Now toxicity we have learned. So let me just give you a quick recap of that. So toxicity are relative stereochemistry of adjacent chiral centers within the mitochondria. So the practical significance um, of toxicity based or exists on the effect of physical properties of body. So for so that's the key thing why we should care about toxicity. And So now let's look at about these three things. So isotactic polymers are composed of isotactic molecules. In isotactic macromolecule, all the substituents are located on the same site in the this macromolecular backbones, and they consist of 100% this mesodiads actually. So what are the diads? So these two, like this way, we can call it as diads. So they are actually meso. Why? Because you have one sigma pairs. So the relationship between these two are meso relationship is there. So that's why they call it as mesodiads, and all 100% mesodiads you are going to see for isotactic polymers. And so now let's look into the physical property. What they in the question the thing is about the property actually, and how they can differentiate. So these kind of polymers are usually semi-crystalline and often form a helix configuration. So that's the ultimate property of this kind of polymer. For symbiotic, here you are seeing already the racemic type relationship should be maintained. Means if one of the thing is R, another thing is S. This kind of alternate rearrangement would be there. So 100% ephemerodiads. So here again, these dyads are 100% racemic. Racemic mixture kind of thing to be present in this kind of relation. And if you see the um, property, so it's crystalline with melting point of 161 degree. So that's about your Tinder tactic. Now let's look at your tactic polymers. So for this kind of polymerization, randomly, so no what we are talking, no relationship or no pattern is there. So the percentage of mesodiads can be between 1 to 99%. So if one of the unit is not maintaining your this particular relation, then only we can call it as toxic diads. And so the thing would be minimum 1% error should be there. So then only you can call this as tactic. Means no such um, no such order is maintained. So for a kind of thing, the property, let's now look at this. So there's just three things what we have seen. So for HFTs, here you are seeing that no such order is there. So it is the racemic diet. So next is again racemic. Now this one is meso diet, and again the racemic. So no order. So racemic meso. So already you have error present, so it is called, that's why it is called atactic. For this case, let's look at, so it is racemic diads, racemic diad, uh, racemic diad, and again, racemic diad. All are racemic diad, and here it is a meso diad, again meso, again meso. So all are meso diad. So that's the way to decide. And so these are the properties. So atactic polymers, polypropylenes are amorphous. Syndactic are semi-crystalline. Isotactic are also semi-crystalline. Difference is the melting point for syndactic is 160 degree, and for isotactic is much higher. It is 184 degree. And let's look at this. So nine. So isotactic is semi-crystalline. Here we have seen that uh, attacks are amorphous again, right option. Symbiotic are semi-crystalline again, right? Symbiotic are also semi-crystalline. is amorphous. So it is was for experiment only these can be removed and uh, the MSC, so A, B, C should be your site options. These three you should select. Now coming to this one, so the maximum number of possible microstructures with respect to position of alkene in poly uh, isoprene in this. So if you use for this particular polymer, so these are the available options actually. With different positions. So let's uh, write that isoprene unit. Isoprene is generally like this is your isoprene unit. Okay? Isoprene unit. Now when it is polymerized, so different things can be taken. The first is so I think the numbering they have given like this way. So the polymerization happening from this kind of relation one means is in the long chain and from this side the polymer is growing like this way. So here actually happening. So one to this way polymer is growing. So then you have going to see this kind of structure. For P4 means if it grows uh, here in the three position. If here that uh, polymer is grows, you can have this kind of microstructure. And if you have one fourth like here and here, these two units here. So firstly, we are seeing this only this one two this double bond is reacting for your polymerization and this impact. It is one type. Or second case, we are seeing this one two is intact, but this particular three four this double bond is participating in the polymerization reaction here. So then you have this microstructure. Now they are saying that carbon one, this uh, first carbon and fourth carbon, they are actually participating in the polymerization reaction, and this here double bond is written. So again, this thing also can happen in it's always on any polymerization thing. So now if you are going to have this kind of double bond. So now two relationship is possible. T short terms. So if it is C, so like this way polymer can grow. This polymer this kind of way, and here like this again this polymer is kind of in this way. So polymer can grow, and you have this kind of structure, and it also can go in the trans manners like this. So for that, you are going to have this particular microstructure. So that's why four microstructures are possible. If one to carbon reacts, if the four carbon reacts, if one for with this relationship, it can nuclear, and one for with so the uh, number of possible microstructure would be four. So four would be should be the uh, right answer for this one, and in that way you can decide. Now coming to this thing. So that Bruchard catalyst system, uh, the ethylene polymerization. So they want to know this thing. So the correct catalyst for Bruchard ethylene polymerization. So the right option would be this kind of system. So palladium-based nitrogen, this kind of system. Uh, this should be your option. So palladium or nickel, this kind of catalyst. So the basic principle for is the chain walking, I think. In the lecture, in the NPTEL lecture, it is described. So I made the facilities with lecture stage. So the thing is, in that way, the chain walking happens. So here you can see kind of a ghosting interaction. Now after that, mm, chain, I think that transfer is happening. Palladium here, it comes, and again this kind of chain walking is there. So let me so this is the initial catalyst, and for palladium based thing is also used like this way. This is one of the examples of that. So the biphenyl unit. So this is the common thing for all Buffers catalyst. This particular ligand is there with different R1, R2, and R3. These things can be added, and also these palladiums different degrees by they also can be ferric, but this particular system is should be present. Biphenyl here, this particular ligand should be there, and this thing for this Buffer catalyst. And for nickel base also, you are seeing that this thing actually for system is kind of unique, and this uh, R1, R2, and R3 they should be varied accordingly, and also extend like this. Now let's just discuss a bit about this chain walking thing. So let me go to that lecture slide. So the chain walking is I think in the this the lecture number 26. There this chain walking mechanism branching it is explained. So for normal branch, what happens is for normal branching. So in the in chain, you can see this metal active site is there, and monomer units can keep coming like this, and the chain can go in this kind of linear fashion. So that's normal branching, normal polymerization. For chain walking, what happens? So here your metal active site is this. So during this process, what happens? This shift happens. That active center fits here, and this kind of system is happening. So that's why it is called that chain walking, because your active side is kind of walking to your macromolecule, and in this way, now if polymerization happens, you can see that obviously the chain, sorry, the branching would be there. Again, this can be longer like this, and again, that metal side can shift, and again, more branching can occur. So that's how the active side can shift its positions like this, and ultimately you can have this a long branching units. So that's how it's called that chain walking mechanism, and mainly branching. So now look at let's look at that uh, mechanism how it happens with metal. So at first, mm, this is your active catalyst. So with one to that alpha, so kind of beta hydride elimination would be there. So at first agonistic interaction and major agonistic interaction leads to beta hydride elimination. So we have learned that already. So metal hydride you have generated, and here you have generated the alkene unit. Now what happens is bond rotation. So this is the side. Now this thing actually rotates like this. So bond rotation happens, and that longer chain unit kind of shifts to the different position like this way. Now when return, so again that hydride transfer happens. Now that metal center, that active center is in this two position, not one position. So initially from one position that long linear thing is happening. Now suddenly that bond rotation happens, and you have this kind of system where the active side of the metal is in the two position. Now again, bond rotation, beta hydride elimination happens, and here you are seeing already that small branch is formed, and the repeating unit would be there, and you are going to see this kind of branching. So metal at carbon 3 stage activation happens, and this kind of thing continues, and that's why it is called actually chain. Sorry, it's called chain walking only branching, and this is the catalyst. So this is the given catalyst itself, what they have given for block polymerization, that non-polar solar these things are used. So this kind of branching is there. So ethylene copolymerization with polar uh, comonomer. So this is the ethylene unit, and this polar heavy unsaturated ester is used for branching and chain walking. And functional groups in non-polar is parts polymer in the material property. So yes, ultimately property you are going to have for with this manipulate so that you can use. So this is yours. Walking polymerization. Now let's go to the next question. So here we have learned that the thing and is option. Now, uh, so these are the some example of phenothiazine type catalyst and the predominant active isomers they want to. So the B is actually your predominant one. And when polymerization is there, you should have one to cis relationship. Then only that polymerization thing can happen. So obviously this A should be removed because here it is trans kind of thing. So this kind of thing should be needed, and this in that in that way it is actually the predominant one. I have made it. I think, mm, so let's go to let's lecture slide where we can discuss this thing. This was thinking. Here it is. So in this week actually these things are discussed. So PI means this kind of catalyst, phenos phenocity means what we are discussing. Another thing is phenoiferous, and this again this kind of thing. So when we want to discuss about this Fi catalyst, so these are the forms that exist, and for catalysis to happen, you need to have this kind of relationship. So one is silent, it's co-catalyst and then this kind of thing. So that's why that fluoros could be speech formation always. And this is the criteria for happening this polymerization. So that is needed. So active site should be C. And in the spectroscopic method, which is in that this kind of these are the basic variations that can be happening with zirconium and this catalyst. In 50, I think we have to have not finished. So these are the options. So O trans and this nitrogen, nitrogen like this. So nitrogen oxygen trans is kind of another way. Another way is nitrogen, nitrogen. This trans thing is maintained like that, and ultimately two fluorols are trans and oxygen, oxygen cis, and another is oxygen, oxygen trans. This particular geometry. So between all of them, for this catalyst, is in that this phenoxy means this way when it is there, that is the predominant isomer, and that's the better catalyst compared to other ones. So oxygen oxygen trans that we need to remember, and we look at here also. It is your options is oxygen trans that way. Now, for Phil's higher olefin process is SHOP. So the active catalyst they want to now the active catalyst one this is the one to be this. So this is the unit and usually is attached to your oxygen and phosphorus, oxygen and phosphorus, and that's olefin units. Where it is the active catalyst one is having that hydride. That hydride should be there. Is that olefin is so olefin and hydride that should be present, which is the important thing for active catalyst for this HOP process. So these are the initial things of phenyl, uh, and phenyl, hydrides, presence of this nickel hydride. This thing actually is important so that thing you can understand with that this mechanism how the thing happens. So the right option is obviously that particular form who is having this nickel hydride. So for this process HOP, the ethylene reacts by the catalyst to give longer chains. Unlike that Sigran-Natta process, which aims to produce very long polymers, the oligomers stop growing after 1 to 10 repeating units of ethylene. So after 1 to 10 ethylene for this kind of catalyst or this SHOP process, you can do that, and that's the difference between that Sigran-Natta process and this SHOP process. So if this stiff form or this stiff catalyst where you are seeing that, so the first nickel hydride and with that ethylene, this thing happens initially the active catalyst form. Then the reduction happens one unit is attached to your hydride and it is with your nickel. So in that way it forms now second unit comes. So again same thing actually repeats like this way uh, with a hydride type elimination and that can reduce this particular thing or particular thing that add like this way and this in that way that chain can grow there in this way and if this hydride elimination happens here uh, like this way then you are going to generate that active catalyst with having this double bond. And again that can second unit can react and it can grow like this. that attaching the attaching thing is happening constantly, and it, it can grow like this, and ultimately you are going to end up with this kind of polymer. So, for this cell olefin process, so the three key factors are there. Step one is oligomerization. So, homogeneously catalyzed clean growth reaction happens of alpha olefin formation. And so, in turn, that alpha olefin is produced like this way. And next is metathesis reduction. So, isomerization of heavier fraction to internal olefin unit. So, your metathesis actually that happens with this, and so they generally produce this LLDP, uh, low branch polymer, and these are the things, and they are internal olefins. This is the general chain length, P10 to C18 units, and lastly, hydroformylation. In this process, we have seen initial process with nickel hydrides. This kind of alpha olefin should be produced, and uh, these things C4, C8, C10 to C18, and 20 plus. So these are the available options, and major thing 40% is C20, C18, and that's the thing it's needed, and that can be these things can be separated by fractional distillation because the boiling points are different, and with this property we can differentiate or purify them. Now, step two is your metathesis. So, metathesis we all know with molybdenum oxide or aluminium oxide, that thing can happen. So, the mix of short and long chain. So, R1, R3. So, uh, let's say in the process you have formed these two particular uh, polymers. Now, what happens is mix of short and long internal molecules. So let's say C4s, they are actually greater than C20, and they are CNTCA for R1 and R2. Now, when that first metathesis happens, so your each of four member unit would be filled with now your C20, greater than C20 long chain unit, and the other thing would be happening. So in that way, the four options are there. So R1, R3. So R1 is initially attached to your R2. Now for that method, this is now attached to your R3 user. So this method happens R1, R3, and R1, R4 is also for stream belts. Is R1, R3, and R1, R4. And obviously there are two options also there. When this happens, then R2, R3, R2, R4, this combination should be there. So this is the second step is which is olefin metathesis. And lastly, hydroformylation is done with that cobalt oxide, sorry, cobalt carbonate. The hydroformylation we all know that uh, um, switch formation from olefin linear hydroformylation. In this particular way, aldehyde at first generated, then it is reduced with this catalyst and ultimately end up with this kind of alcohols. So for plastic gels, fatty alcohols, perfume industry detergent, these are processes which are highly generally used, and in that way can be done. This is for your uh, for we are discussing about this particular olefin. So If you have any question, you can ask now. So after that, we can continue our discussion. Up to this point, if you have any question, just continue. For Dow constant geometric catalyst, so it is titanium 4 obviously. Now let's look at that lecture slide. So this is actually your PGC or constant geometric catalyst, and various donors can be there here like nitrogen, phosphorus, or carbon, and generally bridges are like silicon uh, in this particular base. To improve catalytic activity, molecular weight differentiation that you can maintain and steady regulation and maintaining different ways. So this is your Dow constant geometry catalyst, and here you are seeing the titanium. So that's what we think that titanium-based catalyst they have actually used. So it is a outstanding catalyst. Efficacy or efficiency is 5 to 7 to the 6 kg polymer per kg metal, which explains per kg you are going to have 10 because 6 kg polymer and alpha olefin mo- monomers for incorporation ability up to 60%, high thermal stability, narrow MWD or LLDP for pure mechanical properties and overcome by this thing. Now coming to your mechanism. So this is the way how to react to it in MAO at first sodium chloride at first with methylene group is there and fluoro and it's like this. Uh, and then after that uh, this is your now active site. This thing is generated now. It's here that olefin or monomer unit can be incorporated like this. Then insertion happens. Then propagation step happens. So opening unit can increase and this kind of thing can be processed and titanium hydride would be forming and followed by this thing can happen in that way that we can find. So these are the modified catalyst and examples. So here you are seeing that DHL molecules represented this sorry, published this one which we call nitrogen base. There are half sandwiches actually. So one is sandwich in cyclopropene unit, another unit not. That's why half sandwich thing is mentioned. And here again another examples are there are different examples with variation of different chains and all, and you can see the list of publication with this particular titanium based PGC system. So these are the some other examples for titanium based ones. So where that no metallocene is there, so that kind of thing also are used to absence of metallocenes. This kind of nitrogen based ligand is used and that the options. This one we have to write. So there are some variations that can are in use. And for this, that titanium food, obviously, it's the good one. And for so this one we have read already. The feedstock used in the cells process is ethylene, so that we have read actually. If we show this process, so ethylene is used. So C is your option coming to this one. Yes. So Phillips catalyst for polymerization. For Phillips catalyst, so this actually chromium oxide in silicon. So what happens? So this is the way. one. This is the one. So with silica and chromium oxide, you are going to form this kind of thing, and which is nothing but your active catalyst in terms of silica. So it is example of silica, right? So silica, the best one, and it's the active. Now let's look at how polymerization happens here. So at first, it's activated like this. Um, is produced like this way, and this is the Phillips catalyst, chromium 2. Then olefin is inserted. Now it becomes chromium 3, and then propagation happens like that way. And chromium 3 now it is detached with beta hydride elimination. First form chain, so diene will be forming. So one diene is already there, and beta hydride elimination happen, and to have this kind of scheme. Now followed by this hydride, again this can again do polymerization like this way. And for here you have having chains where one of the so not dying, so ununity will be reduced, and uh another terminal having the double bond. These two ways for this kind of polymerization, and this is the option. So for highest rate of oligomerization for nickel hydride, it is nothing but your this process. So here you are seeing that ethylene is used. So here we can say that ethylene which is having highest rate of polymerization compared to other one. With Dow constant catalyst with the correct option. So low thermal stability compared to metal catalyst. So when you are steam, you have the reduction. So so they are we are here, and we cannot compare. So here we have seen that high thermal stability would be there for this kind of things. So there they are saying it is a low thermal stability, so it is not correct. It's not the right option. Again, these low alpha lysine monoincorporability again uh, basically contradicting what we have learned and saw that high alpha lysine monomer incorporation ability. So it is not right. High catalytic efficacy. So here catalytic efficacy is 20 to the power 6 kg per polymer per kilo of metal. Very high. Uh, is the right one, and for LLDP synthesis. So again, narrow NWD produced LNGP. So for superior mechanical strength. If we check that, that's C and D, we have seen that would be your right option. Now it is for supported metallurgy catalyst for olefin polymerization. So lower activity than your metal unsupported one, then higher MAU is required compared to amount of use for unsupported, and molecular weight of are not affected significantly by using this when it is phosphated. The A, C, and D, that is your option. The lecture slide, if you see, so this supported metallurgy cattle. Let's both they are mm, mm, here you can see it's different type of properties and advantages and disadvantages. You can correlate that, and I think start according to this only. Coming to this last question, so they are just want to know that oxidation instead of titanium. So again, 4 for this one we have shown in that, and if you want beside that also you can use. So it is six ones are there. So the neutral ones, so two things they are plus one, uh, whatever it is plus one, it is fluoro, for plus one, and basically it is neutralized. So with that way you can have that previous state how it is done. So in that way we can do that. So x plus and minus one minus one is equal to zero. Now it's equal to 50. That's how the two way how can simplify, and this one's to be the way to decide them. Now this is I think if this is the best last question. So and if you have read the properties in the next slide, you can do this kind of question. And now if you have any question, you can ask. So, yeah, right. Uh, this particular mechanism. So, for here we is for your SHOP process and nickel-based hydride is needed. This sorry. This uh, particular thing is your catalyst and plastic form with nickel hydride alpha elimination we can think of and after olefin incorporation. Uh, this thing would be for me. Then this thing, uh, one of the olefin unit is reduced, and you have this ethane unit which is attached to your nickel. Now it is in that way it can react like this, and you have a kind of system where the H to nickel bond would be forming like this. Now here what happens is agnostic interaction can be present and beta hydride elimination would lead to this particular. So when it happens, you have now nickel hydride and this thing. So it's your initial unit or active form you can say. So two ethylene units, so one, two, one, two. In that way. In that way it forms. Now it can again incorporate like this or in that way it propagates actually. So second units happen. So you can think of this thing. So it is now like this. So for the reduction, you are going to generate kind of quant. Now the second it is a minus plus and the third ethylene unit one to third ethylene unit scales and it react like this in the same process. This is formed and again beta hydride is there, agnostic interaction. It is very high, so the beta hydride elimination, this thing, nickel hydride regenerates, and this cycle goes on like this. So in that way, this goes on, and one can the repeating unit is there. So that's how this thing happens. So I hope you understand, and okay. Now, any other question if you have, you can ask. Any other questions? I think there we can conclude. And thank you for joining, and we would continue our discussions in the next meeting. We, sometime next Friday, 6 days. So again, thank you.